Alright, this is the spring problem for homework. We have a little picture. Looks like this. There's a spring block here, and then it moves along, and there's like a rough patch of stuff over here. Yeah, that should work alright. Alright, so it says that this mass has a block of some value, 15 kilograms in my case, and then it's accelerated by a spring with a constant of, the spring constant has some value k, and that's equal to some number. After being compressed some distance, x1, that's the distance that it's compressed. Let's write that like this. From the unstretched length, the floor is frictionless except for a rough patch, a distance 2.2 meters long, so it tells us this is 2.2 meters, and it has a coefficient of kinetic friction equal to something. So actually I'm going to call this just D, and then write that as mu sub k, so this will be nice and general. The first question is how much work is done by the spring as it accelerates the block? So as we talked about in class, the work done by any individual force is equal to the integral of the scalar product times its displacement, like so. So we can figure out what that is. So some of you might have said, oh, all right, well, I know what the frictional force is. Frictional force is 1/2 kx squared. So I can just put that in, we'll put in x1 and figure out what that is. The problem with that is is only the force when it's at the maximum compression. And we want to know the force throughout the whole thing. And so this is actually a really interesting scenario, and I already screwed that up, as you might see. It's not 1/2 kx squared. The force is kx. So what you might have tried to do is say, oh, okay, well, the work is just equal to the force times the displacement. And so the force is kx, and the displacement d is x1 here. So this is just x1, x1, and you get something like kx1 squared as the work done on the mass by the spring. And that turns out it's not correct. If you plug in the numbers you have for your problem, you would have gotten that wrong. Because of the fact is that this force is only the force when it's at its maximum displacement. As it moves along here, it changes. It becomes less and less. And the way that we account for that is we actually need to integrate this instead of just multiplying the two things. That's one of the ways. It's not all forces are going to be constant. And so as you integrate this, we're going to integrate this from a position of x1 to 0. So we're taking it at the maximum, initial condition is the maximum displacement to a point where at the equilibrium position. So we're going to put in our information about this particular problem here. So we got the initial condition is x1, the initial position. The final position is going to be when x is equal to 0. And then we put in our information. So this is the direction of F, the direction of this force is actually going to be to the right. So we can put in kx x hat. So that's going to be kx x hat, and that's dotted into the differential length. And we wrote this in class like this. Actually, I'm going to change this. I'll use I hats because most of you in class are going to be using I hats. So I'll put an I hat in here. So this is dx I hat plus dy j hat plus dz k hat. And now we need to do our dot product for these various pieces. So we're going to write out the rest of those steps and write this out just like I had you do this in class. So this is kx I hat. Actually, let's write it like this. We're going to write kx times dx. This is I hat dot I hat plus kx dy I hat dot j hat plus kx dz I hat dot k hat. Alright, so this is an integral across all of these different pieces. It turns out that these two terms are going to go away because, as we talked about in class, the scalar product of two vectors that are perpendicular to one another is going to be 0. And so I hat points in the positive x direction with a unit of 1, with a magnitude of 1. J hat points in the positive y direction with a magnitude of 1. But the angle between them is 90 degrees. So when we take the magnitude of I hat times the magnitude of j hat times cosine of the angle between them, the cosine of 90 degrees is 0. So this term becomes 0 for that reason, because the angles are at 90 degrees. And that same thing is true of this. The scalar product of I hat and k hat are also is going to be 0. So we just get this term, and I hat dotted into I hat gives us 1 because they're in the same direction, so cosine of 0 is 1, and the magnitude of each of these is also 1. So we get x1, 0, kx dx, right? It selects, because the force is in the direction of x, it actually picks out this dx for us. And now when we integrate this, we get 1/2 kx squared. That's just a little bit of calculus, right? That's just doing the integral. x1 to 0. So that gives us 1/2 k 0 squared minus 1/2 k x1. Actually, I'll leave that. It's easier. x1 squared. And so the work done by this particular force is we get minus 1/2 kx1 squared. I don't really like that very much, right? So maybe why did that happen? The reason I don't like that very much is because it says that the work done by this force is going to be negative, and we know that the displacement here, the force is going to the right and the displacement is going to the right, that we should end up doing positive work. So the fact that we got a negative value here is a little bit concerning, and I don't see exactly where I could account for that minus sign. Well, it is true that if I switched my limits of integration here from 0 and x1, that I would get out the right value. But I kind of liked my justification for why I was integrating from this position. Oh, I know why. Because this is 0, and I'm counting this as the positive direction of x. So if I'm counting this as the positive x direction, which is what I was doing, and we call this the 0 point and this as x1, this should actually be minus x1, not 0. Actually, that still doesn't fix it. Because if this is minus x1, this is minus x1, minus x1, minus x1, minus x1. That minus here, that minus sign goes away, so it doesn't even matter, we still get minus. That's troubling. So I can't see my mistake in this particular situation. Clearly I can reason out the fact that this should be positive work. So I'm going to try to work, and I'll post an annotation when I figure out what I actually screwed up. But so the answer here for the amount of net work, sorry, not the net work, but the work done by the spring should be equal to 1/2 k times x1 squared, where whatever value you have for k, whatever value you have for x1. Okay, we'll get the other parts in a sec.